I'm a part-time professor at the Faculty of Bioscience Engineering at the University of Ghent in Belgium in the research group Particle and Interfacial Technology group. And yeah, our expertise in the group is looking at selective separation, also looking more and more in resource recovery kind of topics. So I would like to start very broad, since this is a keynote speech. It starts with climate change, of course, and this is very topical. Oh, upside down. It's a very topical since the summit at the moment in Glasgow. And climate change is responsible for many challenges in a drinking water supply chain. If you look at our traditional water sources being surface water and groundwater, there's a huge challenge in both quality and quantity of these sources as well. If you see on the left-hand side, you see an example in problems in quantity. If you know, in the Netherlands, even this year, we had massive floods in the south of the Netherlands. In 2016, we have massive floods. And the years between, there were droughts. And here you see an example from the Dutch Meteorology Institute in the precipitation deficit in 2020 last year. And you see there's a lot of deficits in the south. Just as an example, of course, it's broader than only the Netherlands, but to exemplify the problem. At the right-hand side, of course, we have also problems dealing with the quality of our sources for drinking water, from industrial waste to more agricultural waste, but also from the urban side of things. There's a deterioration of the water quality. Not only in Netherlands we face these problems, and not only the quality and quantity of our sources for drinking water, we also deal with other problems. And this is a study from the Research Program for Science and Sustainable Development in Belgium. There's an older study 10 years ago looking at the population density in Belgium. And you see here at the site was 2000, so now we're 20 years further. You see Brussels, Antwerp, Ghent, and Walloon kind of cities. And the prospect on the right-hand side in 40 years, there's an immense increase in population density. So more people, more need for water. Except of that, and I will just point it out now, I'll come back to it later. If you look at the urban fabric figures, so the land use, what's land being used in Belgium from the same study, we can clearly see the red spots, that's the urban fabric, very much increasing towards in 40 years. So, four main drivers for the need for alternative water sources. So, apart from groundwater, surface water needs that we have, that we use now, we can tap into other sources for drinking water or for other purposes. We can think about seawater desalination. It's basically quite energy intensive. Rainwater harvesting. There's many examples of alternative water sources. Rain is being very local and temporal, of course. And a very useful other source is water reuse from effluent. And that's the topic of today. Where do we want to use this reused water for? We can think of cooling kind of purposes. For instance, data centers, cooling of data centers use loads amounts of water. Also in the agricultural sector, water reuse for agricultural purposes. And yesterday, I believe a couple of my colleagues from KWR had some presentations about reuse in the agricultural sector. I would like to focus on the reuse in the process industry and even ultimately for drinking water. So these are the two topics that I would like to discuss today. If you look at water reuse already today in Europe, and this is from the DemoWare project from a couple of years back, it's a European Framework Program 7 project, which eventualized the use of reused water. We see it particularly in the south of Europe being quite dominant, specifically looking in Spain, almost 20% of reuse over there. If you go more to the northern countries, and these are the low countries, our countries, the Netherlands and Belgium, you see that the sheer amount is slightly less, but also the purpose for the reuse, while in the south it's more for agricultural reuse. In our cases, it's for ecological uses, for instance, groundwater recharge, or for, in the Netherlands, even more process water kind of reuse. So this is about the context of our talk, and now I made two choices. I present the case of the improved project that we carried out for the last couple of years at the University of Ghent. And we were looking for the reuse of contaminated condensate streams from the process industry. The partners in the program, there are more than here stated, but this was a specific case. This was done for Yara and Sluiskil, together with AIWWW, and it was subsidized by the European Union in the Interreg program, which stimulates collaboration between Flanders and the Netherlands. In the project, there were also other partners like Dow Chemicals and BASF, but this specific case is from Yara. And did it click? No. Sorry. There we go. So the nice thing that we did in this program, we had the lead in this improved project for industrial water reuse, Interreg, Flanders, and Netherlands, to encourage industrial water reuse. And we built some sea containers which were filled with different technologies to treat different sources for process water, being contaminated condensate streams. The next slide is a little animation, a film. I hope it works, and it does. So here you see the inside of our containers, and you can see there are different technologies. In container one, we have ion exchange, ultrafiltration, reverse osmosis on a pilot scale, so on a relevant level. On the container two, electrodialysis and membrane distillation, activated carbon, and advanced oxidation processes. And well, this is a short animation. You can also check it on this website. But here you see the ultrafiltration equipment, the two ultrafiltration membranes, reverse osmosis, coupled or not coupled. It could be operated in series or also in parallel. So a typical 8-inch membrane vertically positioned. And going to the other container, see advanced oxidation processes in which UV peroxide process, so a peroxide kind of injection system, and the UV reactor to manage advanced oxidation processes, electrodialysis. That's also a membrane process with charged membranes driven by a potential difference over the different alternative membranes. Also online TOC analysis, because for condensate treatment, TOC is a very important parameter. And to follow that online, we use this analysis. And finally, we have the activated carbon unit, all in two containers, mobile. And in this case I present, it was localized at Yara Sluiskil, which is in the south of the Netherlands, and is a producer of fertilizers. They deal with contaminated condensate stream, and the question was, is treatment possible to reuse this condensate stream? We tested over a couple of months different streams, and the condensate stream 1, which is a low polluted stream, and typically the composition you can see here. I would like to indicate the TOC levels, which is smaller than 5 milligrams per liter, and the right-hand side, the condensate stream 2, which is much more heavily loaded, up to 700 milligrams per liter, and it was also broken down in a couple of other organic components. So I'll go straight to the results. I don't have much time to go over all the details, but what I would like to show you here is the comparison between operation with electrodialysis, reverse osmosis unit, and I would focus on membrane distillation on this side. And this is the conductivity after treatment. So you see here a line, a black line, which is the indicative kind of a bar that we had to reach. And you can see visually very easily that for condensate stream, the high-loaded and the low-loaded streams with electrodialysis, it was easily achieved. For RO, it was different. It depended very much on the strength of your feed water because there's a fixed rejection of a reverse osmosis kind of barrier. So it managed to get under 200 microsiemens per centimeter for the low-loaded, but not for the high-loaded condensate stream. And if you look at membrane distillation, you will say, well, there's no bar. Yeah, exactly. There was nothing in there. So that had the best kind of quality compared with the other two technologies. On the other side, you also have to look at your water recovery. You want to harvest as much water from your condensate stream as possible. And you can see that for most of the techniques, for both condensate streams, it's above 80%, except when you look at membrane distillation. If you look at these figures, basically we already discussed, you already viewed the product conductivity and the water recovery. I'd like to zoom in a little bit more in on the energy requirement because that's important for an assessment for technology choice, right? So the energy requirement is in the left case for a low-loaded condensate stream, lowest for electrodialysis, but almost highest for the high-loaded condensate streams, which is, of course, interesting and is inherent of the electrodialysis process. So depending on your feed water, your condensate stream, you can make a different choice. But you also have to take into account the capital and the operation expenditure costs. And we made an estimation of that, and then you can see that reverse osmosis is one of the most cost-effective kind of solutions in this case. So to briefly sum up the conclusions, and again I skip a lot of details. RO produced a variable product quality, and depending on your condensate stream quality, you had a different product quality. ED is more flexible and also delivered a high quality in water efficiency, while membrane distillation had the best water quality but had a very low flux, translating into a high capital cost. Alrighty, that was my first example. So the case from University of Ghent. We'll skip now to another example, which is not at the moment. It was an introductory project. And we're waiting now, in hope, fingers crossed, for additional funding for next year, which is the Ultieme Waterfabriek, which boils down to direct reuse of effluent for drinking water. So this is a quite, challenging and controversial, maybe even topic. Well, I'll go towards the steps that we made into this project. So I'll show you first the global water reuse plans in the world. So global map, and this is, you can find this online, the Global Water Connections map, and it shows us the water reuse plans all over the world. Not all of them, some are missing, by the way, but it gives a nice overview. You can directly see that in the USA, in the US, there's a lot of reuse plants. Outside of the US, they're much less. There's one, there are a couple in Australia. There's only one indicated. This one is Singapore, the famous Newater plant. This is one of the first one, the Goan Gap facility in Namibia, Windhoek. And the only one in Europe is the one in Belgium. And I'll come to that later. I have a slide for that. What is striking, if you look, and this comes from a recent publication of us, please only look at the lower side of the graph, because the publication was also about membrane technology and its development. So you see here a timeline from 1960s, previous century, towards approximately now. And here you see some points where reuse plants in the world were constructed. A couple of things we can learn from this graph is it's not new. It started already, what is it, 60 years ago. So reuse of water for drinking water purposes is definitely not a new thing. It's Water Factory 21, California, and then it started increasing in size. There are more plants dealing with this reuse, and they become larger. So I made a small overview of all the plants, and it's impossible to read, of course, but that's not the point. Oh, shit. Okay, sorry. Oh, boy. Okay. So I summed up the projects, where they are situated, countries, the size, so the capacity, I'll say, when it started. So I organized it since 1962 until 2021. These are the schemes, which kind of technology is used. And this is an interesting one. Is it indirect or direct potable reuse? The difference is that the produced water in an indirect potable reuse plant is going through a natural buffer, being either a reservoir or an aquifer, but not directly. So I have to speed up a little bit. Looking at what we learned from this whole table, 8 out of the 37 ones of the plants are outside the USA. So most of the plants, I already said that. One is in Belgium, and that's the Torele intercommunale waterleidingsbedrijf van Veurne Ambacht. Luckily now easier, Aquaduin, in Belgium, in Kokzijde. This is a plant that's already 20 years in operation without a lot of trouble. And the scheme is simplified microfiltration, reverse osmosis, and advanced oxidation. Again, 20 years already without massive problems. If you look on all the technologies. So back to the scheme I just showed you. I just counted the number of schemes with reverse osmosis. There are approximately 70%. The ones with activated carbon being granular or biologically active, approximately 30%, and 30% with advanced oxidation or UV technology. And of course, sometimes in combination. I mean, it doesn't add up. It's not either or. I think this is my last slide. Yeah, Luc was just about to stand up. So, and that brings me to our project. Very brief. Jelle Roorda tomorrow has a presentation also here on this platform, and we'll talk a little bit more about this, about the project on the Ultieme Waterfabriek, in which we are looking for direct potable reuse. One of the advantages of that is efficiency of land use. Remember one of the first slides I presented, the dark red spots on the Belgium map. This is a more efficient use of land. Basically, the wastewater treatment plant, and this is an idea we have for the Ultieme Waterfabriek process stream, concentrate stream. And there's a lot of partners involved. It's a Dutch initiative, like 9 or 10 water boards are on board. A couple of, how much? 5 water companies, and a couple of research institutes. And that's it. Thank you for your presentation.
Thank you, Emile. Maybe I can start with a question. You talked about direct reuse for drinking water. We all know that globally, let's say, industrial water and agricultural water is the highest consumers are the highest consumers in water resources. So, is it not better to think of integration, reclamation for industry instead of reclamation for direct water use or direct drinking water use?
Yeah, that's a good point. I think it's not either one or the other, because you can produce from plants that we are looking into it in a certain water quality for multiple purposes. So with an additional step, remineralization, you can make drinking water from it as well. So it's more and.
Okay. Okay. Other questions? 1 or 2? No questions? Everything clear, Roos?
Good.
No? No?
No problem.
Yeah, thanks, Natalia Duque from Switzerland, from EAWAC. I was just wondering, why do you think it's not like the case that Europe has more recycled plants, or like what's the limitation here?
The question is why there is more reuse plants in the south of Europe?
No,
Yeah, like why is it only kind of mostly in the US and not yet like in
drinking water, the drinking
for
water.
drinking water? That's a good question. I wouldn't. Yeah, it probably has to do with regional kind of necessities and also cost of things. I mean, more money available, readiness. As one of the previous speaker told us, for instance, in California, there's a lot of readiness to look into this kind of options. So that has to do with public perception, with available cost infrastructure, etc., necessity, all these kind of things. And in America, they come together at certain spots. As not everywhere in America, specifically in California. There are a couple of plants also in Texas, also a very dry state. Miami, there's more to do with the money. That's okay. So different drivers, I would say.
Okay.
Yeah, lack of water resources, yeah.
Yeah, but in Spain as well. But
In
maybe
Spain,
good to study, I think. So thank you very much, and Emile, for your introduction.